All right. At this point, we move into section 10.10 and one of my favorite applications of power series, which is evaluating non-elementary integrals. As I probably mentioned a long time ago, most functions do not have any simple antiderivative. And the function that you see here is one example, e to the negative x squared. You can try every trick in the book and you will never find an elementary antiderivative for e to the negative x squared, which means there's really no hope of finding an exact value of this integral using the fundamental theorem of calculus, where you just find the antiderivative and plug in 0.1, plug in 0 and subtract. Okay, but the next best thing is that you can estimate the value of this integral to any degree of accuracy that you need by using a power series. All right, so in this problem, we're going to use a series to approximate the value of this integral with an error of magnitude less than 10 to the negative 8. All right, so let me show you how that works. Switching back to the tablet. Okay, so the first thing we need is a Maclaurin series for e to the x, which we have. E to the x is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial, et cetera, et cetera. Okay, so now if I replace x with negative x squared, like we were doing earlier, I will have a series for e to the negative x squared. All right, and that series will look like 1 minus x squared plus the square of negative x squared over 2 factorial plus the cube of negative x squared over 3 factorial plus the fourth power of negative x squared over 4 factorial. In other words, 1 minus x squared plus x to the fourth over 2 factorial minus x to the sixth over 3 factorial plus x to the eighth over 4 factorial, et cetera, et cetera. All right, so now I'm going to integrate that series term by term. So the integral of e to the negative x squared with respect to x, that series is going to start out x minus x cubed over 3 plus x to the fifth over 5 times 2 factorial minus x to the seventh over 7 times 3 factorial. You see what I'm doing there? Just using the backwards power rule. Plus x to the ninth over 9 times 4 factorial. All right. So then, oh, you know what? Let's do this. Because what we're really after is the definite integral, right? So now if I just stick a couple of limits of integration on this from 0 to 0.1, what I would be doing then is evaluating this series at 0.1 and then subtracting the value of that series at 0. Okay, so I think I can squeeze that in down here. That's going to go 0.1 minus 0.1 cubed over 3 plus 0.1 to the fifth over 5 times 2 factorial minus 0.1 to the seventh over 7 times 3 factorial plus 0.1 to the ninth over 9 times 4 factorial. And then I don't have to worry about 0 because every single term of this series at 0 is 0. Okay. So now think back a couple of sections to when we talked about alternating series. If you want to estimate the value of an alternating series with error less than, say, 10 to the negative 8, you just have to find the first term whose absolute value is less than 10 to the negative 8. And then that's going to be the first term that you don't use. Okay. So what I'm going to do now is bring up my calculator. All right. And so I don't think it's going to take us very long to find the first term whose absolute value is less than 10 to the negative 8. So I'm not going to bother using the table because in order to use the table, I would have to have a closed form expression for the nth term of the series, which we could find. It wouldn't be that big a deal, but okay. So obviously 0.1 is not going to work, and I'm pretty sure 0.1 to the third over 3. Oops. Well, it's not going to work if I do it like that. I'm all thumbs today. Darn it. Okay. There we go. So that's not going to do it. The next term, or I should say absolute value of the next term, is 0.1 to the fifth divided by, notice I have to put this in parentheses, 5 times 2. It's 2 factorial, so I could just write 2 because 2 factorial is 2. Okay, but let's do it properly. Okay, that's 1 times 10 to the negative 6. We're getting close. Actually, I think the next term might do it. Let's see, 0.1 to the 7th divided by, let's try that again, 0.1 to the 7th divided by 7 times 3 factorial. All right, that term is less than 1 times 10, or is less than 10 to the negative 8, right? This is 2.38 times 10 to the negative 9. So this is the first term that we do not have to use. So actually we can approximate the value of this integral by using just the first 3 non-zero terms. So let's go back to the tablet. Or actually, you know what? I don't think we need to go back to the tablet. Let's just figure out what that is. So 0.1 minus 0.1 to the third divided by 3 plus 0.1 to the fifth divided by 5 times 2 factorial is equal to 0.09966676667. And because we know that value is accurate with error less than 10 to the negative 8, I think that means the first 7 decimal places at least are good. All right, so that's how you can use a series to approximate the value of an integral. All right, so the last thing we're going to look at in this video is using our new friend table 10.1 to find the sum of these series. So the trick in this kind of problem is to match the given series with a series in table 10.1 and just kind of, try to figure out how the series from table 10.1 has been tweaked to give you the series that's given in the problem. All right, so going over to the tablet. Okay, the first thing we have is this thing here. All right, so when you look at table 10.1, the first thing you want to do is pick out a series that has more than just odd or even number terms. So that eliminates sine x, cosine x, and inverse tangent of x. All right, and if you stare at this for long enough, you start to notice a couple of things. First of all, well, basically it's that this series can be written like this. You've got a 1/2 here, and then it's minus 1/2 times 1/2 squared plus 1/3 times 1/2 cubed minus 1/4 times 1/2 to the 4th. All right, et cetera, et cetera. So that we have a series that looks like that. This is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 where x has been replaced with 1/2. All right, and the series that you're looking at here is the series for natural log of 1 plus x. Okay, so that means we want to replace that x with 1/2. And so it turns out that this series converges to the natural log of 3/2. It's kind of cool. Right up until now, the only types of series that we've been able to find the exact sum of are geometric series and telescoping series. Okay, so for the very last example in chapter 10, we have this thing, x squared minus 2x to the 3rd plus 2 squared x to the 4th over 2 factorial minus 2 to the 3rd x to the 5th over 3 factorial, et cetera, et cetera. So the first thing I notice about this is that it doesn't start until x squared. In other words, the degree 1 and 0 terms are missing. So that's kind of fishy. We don't have any series that look like that in table 10.1. But then after that, all of the other terms are there. Nothing is missing. So what I'm going to do first is I'm going to factor out an x squared. Okay, because then inside I'll have a series that starts with a constant term, which is the type of series that we're more used to seeing in table 10.1. So that'll give me x squared times 1 minus 2x plus 2 squared x squared over 2 factorial minus 2 to the 3rd x to the 3rd. See, doesn't that look nicer? 2 to the 4th x to the 4th. All right, and I can take it one step further. Okay, instead of writing 2 squared x squared and 2 to the 3rd x to the 3rd and all that, why don't we write it as the square of 2, or actually, notice how the signs are alternating. The way we can make that happen is to put a negative 2x in here. Right, because all the positive degree terms are what am I trying to say? All of the even degree terms are plus and all of the odd degree terms are minus. Okay. All right. So now, darn it, I just have to look for a series that looks like this. All right. Well, that kind of looks like the series for e to the x with the x replaced with a negative 2x. And so I think the sum of this series is the function x squared times e to the negative 2x. All right, and that's going to do it for sections 10.9, 10.10, and that's going to do it for chapter 10. Woohoo! We'll see you next time.